Hello everyone, welcome to lecture 12 on Mechanics and Materials 1. In this lecture we want to talk about torsion. This is our first lecture on the topic torsion and we have 4 lectures on this topic. So this is the first part of the 4 parts. In particular, we cover sections 5.1 and 5.2 of the book and they correspond to the 5th chapter of the Hibbeler book. So before I talk about torsion, I want to remind you of the big picture of mechanics and what we are doing here in Mechanics and Materials 1. What we want to do is always to find a relation between deformation and loading. And if you remember, we said that this question that is the big or the key question of mechanics and materials, it cannot be easily answered at this stage. What we need to do is to define a suitable deformation measure that we call strain, and then we define a suitable load measure that we call stress, and then we learn that between stress and strain you usually have the so-called constitutive law or constitutive response of material or material law, or usually we talk about Hooke's law, and then using that connection we can find a relation between deformation and loading. So that's how we do this. Now for axial loading, the deformation that we are looking for is delta, is the displacement essentially. The loading that we are talking about for axial loading is a normal force or a normal loading, let's say P. And the corresponding strain in this type of problem would be normal strain. And then the normal strain is defined as delta divided by L, L being the length of a member. Then for stress, also we would have normal stress for this type of problem for axial loading, and stress or normal stress sigma would be defined as force divided by area. The relationship between normal stress and normal strain is the Hooke's law, so sigma equals E epsilon, with E being the Young's modulus or the modulus of elasticity. Okay, if you put all that together, then you find the answer to that question. So to that big question that we wanted to find the relation between delta and P, well, that is delta equals PL over EA. So we have now that relationship. But that was for axial loading. Now what we want to do now is to look into a different problem, and that's a torsion problem. And it's essentially in a torsion problem we are looking at a picture like this. The picture shows a rectangular block under torsion, and then under 90 degree, 180 degree, 270 degree, and 360 degree rotation or torsion. So this is the type of problem we want to look at, but I also need to tell you that the picture you are looking at, it shows a torsion of a rectangular block. What we want to do in this course is to look into cylindrical block. Okay, so I use this picture because it looks more interesting, but remember that we are looking at cylindrical bars basically, or cylindrical shafts. Okay, so now if we want to look at the problem torsion from the perspective of the, let's say, big picture of mechanics, now again we want to find a relation between deformation and loading. But now deformation for the torsion problem, for a torsion problem, the deformation that we are talking about is an angle of twist or twist angle. So we are not looking for something like delta as before, we are looking for something like phi, that would be an angle. And then the type of loading that we are interested in is not a normal force P, is something like a moment or a torque. Okay, so we would have torque, we would have phi. Now, for this particular problem, then we need to find out what would be the strain measure that could help us to answer this problem, what would be a suitable stress measure and what would be the corresponding material law or constitutive law between stress and strain. And then if we answer all those questions, eventually we can answer the final question here. So torsion is the formation under the application of a torque. So what is a torque? A torque is a moment that tends to twist a member about longitudinal axis. In order to illustrate torque, I start with axial loading again because it provides a good reference for us. So if you assume you have a rectangular block here or a bar, on that bar, if you apply a force, a normal force, P, then we talk about the axial loading. So remember, we are talking about the problem that you apply a force, but also the force is normal to the cross section. So this leads to an axial loading problem. Now, on the other hand, if you apply a torque, a moment, but a moment with respect to longitudinal axis. So I am using two arrows instead of one arrow, indicating that it is not a force, it's a moment. So basically, it's a moment that wants to cause a rotation of the block. Then we call this a torque. And the problem that we have here is torsion as opposed to axial loading that we had here. Now, it would be enlightening to also bring the bending problem into the picture. If you had bending, bending is in a way similar to torsion because the loading that you apply is not a force. The loading that you apply is a moment. But now, for a bending problem, that moment is with respect to a different axis. So if it was with respect to this axis, now this would be a bending moment and this would be a bending problem as opposed to a torque and a torsion problem. All right, so what we want to do in this lecture and in the next 3 lectures is to talk about this problem. All right, so this picture shows a cylindrical block under external torque T. And then again, pay attention that torque is essentially a moment that is applied with respect to the longitudinal axis here. And as I mentioned before, we are only interested in cylindrical members or cylindrical shafts for the majority of these lectures. All right, so what we want to do is to calculate how much twist we get because we apply this torque. Similar to the axial loading problem, we can assume that the other end is fixed for simplicity. Usually you don't have to assume that. Basically what you want to do is always to calculate the response from A to B. But you can imagine if at point B this thing is fixed, then it's an easier problem to look at. Okay, so ideally we are looking at this problem, but again, for simplicity, we just assume that it is fixed at the other end, similar to what we have done in the previous problem, in axial loading problem. Now, you define the coordinate system x, y, z, and if you sort of look at it from the side, it looks like this. So again, using two arrows, it shows that it's a moment. It's not a force. And the x-axis starts from, or let's say the origin is here where it's fixed, and then the x-axis aligns with the longitudinal axis of the shaft. So you can imagine under application of the torque now, you would get a twist in the member. So if you look at this member now, it's going to deform like that. And essentially you can imagine that at the base where it is fixed, the angle of twist would be 0 because you would get 0 twist. And then maybe you can sort of, from the picture, you can imagine that the further you come, the angle of twist will increase. In other words, you can assume that the angle of twist phi is a function of x. Okay, so you can see that from the picture. We will need to make some assumptions to make sure that this holds, and we will talk about those assumptions. But for now, just remember this is sort of the big picture that we are looking at. And then for this type of problem, remember the phi is essentially what we want to relate to the torque at the end. So that was the big picture that we want to solve. This is what we want to do. Okay, so if you look at the shaft before the formation and after the formation, the first assumption that we need to make is that the radial lines remain straight. Okay, so let's say you have this shaft under the formation. Now, if you look at any cross section and if you look at these lines, we assume that they remain straight. So obviously you get a rotation. So basically, if you think about a point that it was here, now in the next picture it's going to be here. So you get that much rotation from somewhere that it was. But we assume that in that cross section the radial lines remain straight. So this thing does not happen, and this is what is happening. Okay, so this is our first assumption. The second assumption is that circles remain circles, and again, as I mentioned, we talk about cylindrical blocks, so it makes sense to talk about cross sections that are circular at the beginning. But then the assumption here is that even after the deformation, the cylinder remains a cylinder. So basically, the circular cross sections remain circular cross sections. Another assumption that we make is that longitudinal lines become twisted, but they remain straight. So you can sort of see these lines in white here and in red here. So these are the longitudinal lines, and as you can see, they get twisted, but they remain straight. Now, the consequence of this is that you get equal twist at the same x. So for the same distance from the base, you get exactly the same amount of twist, and this is a property that we want to exploit later. The last assumption that we make is that cross sections remain flat. So you don't see a warping or bulging of a cross section. So basically, if you look from the side, every cross section remains exactly where it was. Okay, so if you make these assumptions, now, if you look at the picture that we just had before, you can imagine that we would have an angle of twist, phi, and that angle of twist, as we mentioned before, it would be a function of x, because again, you can imagine that at the base, you should get 0 twist, and then the further you come, it will increase. So possibly you can imagine also that at x equals L, the angle of twist is maximum. And then again, this intuition is very much related to the assumption that we made here. So what we want to do is to find a relation between the angle of twist and torque. So if you look at the shaft again and sort of we enlarge it here, imagine that the length of the shaft is L, and then we have the x coordinate starting from the base, and this would be our angle of twist at L. But also if you look at those lines, the longitudinal lines, let's say you had a line here, the white line that it was before the formation, and then you twist it, so you get the red line. Between the two lines, you also get this angle, and we want to call that angle gamma. And I intentionally call that angle gamma because I want to remind you of shear strain. We will see shortly that this is exactly the shear strain that we talked about before. So now if you look at these two angles, angle phi, so this would be angle phi, is a function of x. So you can see at different cross sections, at different x, you get different angles. But the other angle, gamma, is not changing with the cross section, but it is changing with the radius. So you can see, for instance, if you look at this angle, it doesn't matter at which x you are looking at, it's the same angle. Okay, so it's not a function of x, but you can also imagine that at the center, this angle would have been 0. Now, if you look into these two cross sections, on the right picture, on the left picture, you can see that now if this was before the formation, so before the formation, if you start with that rectangle, after the deformation or after you apply the torque, that rectangle would move to a parallelogram as it is shown here, and this is exactly what we had in the shear strain problem. And then again, if you remember, we call that angle gamma shear strain. So we look into this picture again, and if you pay attention to the arc at the cross section at the end, you can do it for any cross section, but let's just look at this particular cross section at the end. If you look at that arc or that arc length, now the length of that, you can relate it to the distance from the center here and the angle. So this would be R max, and we call R max also C. So C is just another letter for R max. So you would have R max times angle of twist at L, which is exactly that arc length, equals, now if you look at this other sort of triangle here, if you look at this one, then you can see that would be also equal to L, the distance, times the shear strain, the angle gamma. And then again, if we look at the arc, which is at the end, that gamma would be also gamma at R max. This relation is extremely important, as we will see in the following. So keeping that in mind, now we want to look what happens inside the bar. So what we want to do is to take this bar and then cut it at a distance x with a, let's say, with an incremental length dx in the x direction. So if I enlarge that particular part, and then again it's a 3D picture, so what you see here in front is what you have here, just in front. But you can imagine there is this other dimension which goes inside, and that would be our dx. And also pay attention that I am cutting that little cross section at a distance r from the center, which is less than maximum r or less than c. So now if we look into that, again, similar to what we had before, if you think about this rectangle before the formation, the rectangle would shift to this parallelogram after the formation. And then again, you remember that angle that we have between the two is exactly shear strain. Now we play the same game we played before, but now we play it only for a little cross section. So if you look at this arc length again, you can imagine this arc length is the distance r times angle d phi, but also it's equal to the angle gamma times the distance, let's say AB or AB prime, which in this case is dx. All right, so you get this relation, you get r d phi equals gamma dx. And then again, just to make it clear, remember that the picture that you see here is just a more standard representation of what we had before. Okay, so to sort of clearly show that the angle here that we called gamma is indeed shear strain, and the problem that we are looking at, okay, it's a torsion problem, but the type of strain that you need for a torsion problem is shear strain. And you should compare this with axial loading, because for axial loading, the type of strain you needed was normal strain. Okay, so if you had axial loading, the type of strain that you had was epsilon, was normal strain. But you can see that for torsion, the type of strain that we are having is shear strain, gamma. Okay, and then if you just reorder this relation that we just had before, you can see that gamma shear strain is equal r d phi over dx. And now if you remember, we assumed that straight lines remain straight. They twist, but they remain straight. And if you remember, we said that that assumption essentially tells us that d phi over dx is a constant value. In other words, whether you call that d phi over dx or whether you call it phi at L divided by L, you are talking exactly about the same value. It's the same constant, it's the same ratio. All right, so we have this relationship already. So we know gamma is equal r d phi over dx. We know that's constant, and we know that constant is the same as gamma divided by r, or is the same as gamma max divided by c. So again, you can sort of write it in a different order. So basically, this is what we do here. We know this thing is constant. So d phi over dx is gamma divided by r. And then because gamma divided by r is equal to d phi over dx, then that is also a constant. Okay, so d phi over dx is constant. That tells us that gamma over r is constant. That's basically what we know. Now, if we know gamma over r is constant, that means gamma max divided by r max is also constant. Okay, so that gives us this relation that basically tells you gamma equals r over c times gamma max, or you can say gamma equals r gamma max divided by r max. So again, r max is just c. Now, gamma max divided by r max is constant. That tells you that gamma is just proportional to r. So it's a function of r, but it's also linearly proportional to r. And basically that tells you that if r is 0, gamma is 0, which makes perfect sense. Again, if you sort of think of the picture that you have here, you can imagine that this is for the outer layer, but if you look inside, so if you go further down, at different r, you have a different gamma. Okay, so you get the maximum gamma if r is maximum. And then if r is less than r maximum, you get a gamma that is less than gamma max. And eventually at r0, you get gamma equals 0. All right, now that we have a relation for shear strain, and we know that this torsion problem basically deals with shear strain, we connect shear strain to shear stress, and we know shear stress tau is related to shear strain via shear modulus G. So tau then is G gamma, and tau max is G gamma max. And then again, using the relationship that we have here, you can say that tau shear stress is R over C times tau max. What does that tell us? That tells us that the shear stress distribution is linear. It tells us it is 0 at the center and its maximum at the outer radius, where the radius is maximum. And also you remember this is shear stress. So basically shear stress always works on an incremental area, let's say dA. And then if you want to think of the force corresponding to that shear stress, you should always think that dF is shear stress times dA. That would be a shear force. All right, so now we have a relationship for the distribution of the shear stress in the cross section. But remember, the problem that we had from the beginning, or the question that we want to answer, is what is the relationship between the twist angle and T? So the torque is the key quantity that we are interested in, not the shear stress per se. Now, the torque, the total torque that you have on a cross section, you can imagine is the integral of dt, and then dt in that relation is r df. So it's exactly the moment due to each incremental force. So the moment of an incremental force with respect to, let's say, axis x, with respect to the longitudinal axis, would be the distance times force. So what you want to do now is to calculate the torque by integrating distance times force over the area. And then again, we remember that shear stress is shear force divided by area. So shear force dF would be tau dA. which we will use here. And then for tau, that is shear stress, now we use the relationship that we derived before. So if you do that, now you would have this integral. In this integral, tau max and c are constant, and then again, remember c is the maximum radius or the outer radius of the shaft. So you can take them out of the integral, and if you do that, then you end up with an integral which looks like integral of r squared dA over the area. Now this integral may look familiar to you, and that's because it's exactly the polar moment of inertia that you may have seen in your other courses. Now, if we call this polar moment of inertia J, so we show that by the letter J, then the relationship that we get for torque is torque T equals tau max, maximum shear stress, divided by C times J. Before I proceed, I want to talk about the moment of inertia a little. So you should not confuse the polar moment of inertia J with the moment of inertia that we have later, and we call that I. And also similar to that, we had moment of area. So we had our first moment of area, if you remember. Qx and Qy, we call them moment of area. So if you think of them as first moments of area, because you have just the distance times area. Now, if you have higher powers, if you had power 2, you would talk about second moment of area. And that second moment of area connects more to something like moment of inertia. Okay, so you should not confuse this. They have similar forms, but Qx and Qy, we had it at the beginning of the course. These are just the moment of area, or again, the first moment of area. Then we have polar moment of inertia J, and we also have just moment of inertia I that we will use for bending problems later. Okay, having said that, we can summarize what we have so far. So T, torque, is the integral of distance times force over the area. And if you define the polar moment of inertia as the integral of r squared dA over the area, this is the relationship we get for torque. And then if we reorder that relationship, now we can express tau max in terms of torque. And also remembering that the shear stress itself is, let's say, a linear distribution, or is linearly proportional to tau max, you can calculate also the shear stress. Okay, so the question is really sometimes what is given and what you want to calculate. So if you imagine that torque is something that you know, and then you want to calculate the shear stress, then this is the relationship you are looking for. So this is exactly the key relationship that you need to remember. So tau equals TR over J. Shear stress equals torque times radius divided by polar moment of inertia. So the next thing we want to do is to compute the polar moment of inertia J for circular shafts. And then again, circular shafts are the only types of shaft that we are interested in for this discussion here. So first, think of a solid shaft. So solid shaft in the sense that it is not a hollow cylinder, it's a full shaft. Now, for that one, if you want to calculate J is the integral of r squared dA over the area. Now, dA, if you look at a circular shaft, you can write dA as 2 pi r dr. And if you do that, then instead of integrating over A, you can say that you want to integrate from R0 to R max. And by doing that, you get the relationship here. So eventually you can calculate J for a solid shaft as follows. So for a solid shaft, J is pi over 2 C to the power of 4. Now, if you have a tubular shaft, so it's a hollow shaft, you do exactly the same thing, except that now you integrate from Ci to Co, indicating that you integrate from inner radius to outer radius. And if you do that, then for a hollow shaft, for a tubular shaft, you get J equals pi over 2 Co to the power of 4 minus Ci to the power of 4. And then you can imagine if Ci is just 0, then you recover the solid shaft, the full shaft. Now, an interesting example to think about is that what happens if the inner radius is half of the outer radius? So if we want to compare a solid shaft with a tubular shaft such that for the tubular shaft Ci is half of the Co, then the polar moment of inertia for tubular shaft is almost 94% of the solid shaft, because pay attention that this goes with the power 4. Okay, so if it is only half, if Ci over Co is just half, that ratio to the power of 4, that gives you 1 over 16. So basically that means if you use a hollow shaft with this dimension, you can recover up to almost 94% of the same J that you would get for a solid shaft. Now, why is that interesting? Because if you calculate the weights of the two shafts, you can imagine that the weight goes with the power 2 of the radius because it relates to the area. So basically the tubular shaft would have more J for less weight. Okay, so basically you can save from the weight, because the weight goes with the power 2 and J goes with the power 4. So basically by using a hollow shaft, you can have a more economical design. In other words, you can basically cut 25% of your weight, but you cut only 6% of your polar moment of inertia. And if you remember, that polar moment of inertia immediately relates to your torque. So that means hollow shaft is possibly a better shaft design for usual torsion problems. Okay, the last topic we want to talk about in this lecture is about the distribution of the shear stress itself. And it's quite interesting because you may think that if we apply a torque on a certain cross section, so if you think of this cross section here, you would obviously imagine that there is a shear stress on the cross section itself, as we just showed before. So yes, obviously there is a shear stress on the cross section. It is maximum in the outer wall, it's 0 at the center. So you know there is a shear stress. That's good. But then the question is, what happens in the other direction, in the direction that is inside the bar itself? And that direction is shown here, and I'm going to sort of enlarge that picture. So if you think of the shear distribution, shear stress distribution that we had, we said this is a linear distribution, so that's what you have on the cross section itself. But if you cut that piece and you look what happens to those little cubes, you can actually imagine that because of what we discussed before, if you have a shear stress in this direction on a cube, you need to have one also on the other side. Okay, so you get also a shear stress in the longitudinal direction, not just on the cross-sectional area itself. So in other words, not only shear stresses, not only we get shear stresses along radial lines of the cross-section, but also we get shear stresses along axial planes. And then again, this is exactly due to the moment balance, or due to the equilibrium of moment, as we discussed before when we talked about shear stresses. Now, an interesting consequence of that is that you can imagine that if you take a piece, if you take a specimen and you apply torque on it, now because you have shear stress in that other direction, in the longitudinal direction, although you are applying a torque, it could fail in the longitudinal direction. And that's exactly what happens. So this is a failure of a wooden shaft due to torsion as shown in the picture. And then again, this is exactly related to the discussion that we had here. You apply a torque, so obviously those cross sections themselves, they have shear stress distribution, but also you get shear stress distribution in the other direction, and those shear stresses, they could also lead to failure. So this is an indication that those shear stresses actually exist. The exercise that we are looking to in this lecture is similar to problem 5.2 on page 190 of the book. The shaft shown in the figure is supported by two bearings at its ends and is subjected to 3 torques. So you have the shaft here, there are these 2 bearings, and you have 3 gears on which you apply the external torques. Determine the shear stress developed at points A and B located at section AA of the shaft as shown. So you have section AA here, and on that circular shaft you have 2 points B and A with different distances, and you are asked to calculate the shear stresses developed at points A and B. So the first thing we need to do is to essentially cut the shaft at section AA and draw the free body diagram to compute the internal torque, or the torque at section AA. That's what we want to do. So we know we have bearings at the ends, so bearings apply no torque. And if you cut the shaft at cross section AA, whether you cut it from left or right, it doesn't matter. Let's say we cut it from right. So what we see here is that this is your cross section AA, and this would be your direction X. Now on that cross section you get a torque TA, and then again I am showing this in a counterclockwise direction such that it's essentially positive. So whether you call it MA or TA, it doesn't matter. It's a moment, but it's torque because it's a torsion problem. Okay, so you write the sum of moments with respect to x-axis is 0, and assuming that this is your positive direction, and this would be your counterclockwise direction or a plus direction, then you get plus dA minus 3 because it's in the opposite direction, it's in the clockwise direction, plus 4.25, again with a plus because it's counterclockwise, is 0. And that gives you TA equals minus 1.25 kilonewton meter, which means it's 1.25 kilonewton meter in the clockwise direction. So this direction is not good. This is actually, this is what is happening. Okay, it's in the opposite direction, which is clockwise, and it's 1.25 kilonewton meter. So then for the cross section, we calculate the J, the polar moment of inertia, and that is, if you remember, it's pi over 2 c to the power of 4. C is the maximum radius or the external radius, and for the problem that is 75 millimeter. So we can calculate J. Then from the relations that we have, tau equals TR over J, we can calculate the shear stress for points A and B. So pay attention that points A and B are at different distances from the center, so they have different radius, but they are at the same cross section, so they have exactly the same torque, and it's the circular cross section, or it's a uniform cylindrical shaft, so J is also the same. So basically that's the relation, and if you insert the values, you get shear stress at A to be 1.89 megapascal, shear stress at B is 0.377 megapascal. Now, if you want to look at the direction, again, remember that the torque that we have at that cross section is clockwise. That means the forces or the shear stresses that you would have at that cross section, they would also be in that, let's say, clockwise direction. And obviously there would be a sort of linear distribution. So at the outer radius, you get the maximum, and then you get 0 at the inner radius. That's essentially what we wanted to calculate for this example. All right, so this was our first lecture on our lecture series on torsion. We have 4 lectures, so we will have torsion 2, 3, and 4 to cover in the coming weeks. I'll catch you in the next one.